Welcome to the lecture series on CFD, Part 2. This is Lecture 22 on finite difference methods for non-orthogonal grids. Finite difference methods are usually used only for moderately complex geometries and either with structured or block-structured grids. Most published methods use coordinate transformations to convert the Navier-Stokes equations from Cartesian to non-orthogonal coordinates, but there are also other possibilities, of which we shall mention one. An unusual feature of transport equations written in non-orthogonal coordinates is that they contain mixed derivatives in diffusion terms. Approximation of mixed derivatives requires special care if grid non-orthogonality is severe. If Cartesian vector and tensor components are used, coordinate transformation can be hidden. That is, one does not have to assign values to non-orthogonal coordinates or compute the Jacobian of coordinate transformation. We shall show how this can be done. Finite difference methods can in principle be applied both to unstructured grids and to a cloud of discrete points in space without the need to define a grid. We shall describe how this can be done using shape functions. Finite difference methods are not widely used in engineering. All commercial CFD software is based on finite volume or finite element methods. However, finite difference methods are used in research for some applications where higher order discretization is required, for example, in geophysical problems. It is much easier to develop higher order finite difference than finite volume methods, because only derivatives at one point need to be approximated in the former, while the latter requires approximations of surface and volume integrals, interpolation, and differentiation at multiple points per control volume. Finite difference methods are usually based on coordinate transformation, which is typical for structured or block-structured grids. An alternative is to use shape functions fitted to a certain number of grid nodes and differentiate the shape function to obtain approximation of derivatives as a function of variable values at grid nodes. This approach is also applicable to unstructured grids. Methods for approximation of derivatives described in lectures 4 and 5 for Cartesian grids are applicable also to structured non-orthogonal grids. The curvature of grid lines is accounted for in the Jacobian of coordinate transformation. When structured grids are used, each grid line can be interpreted as a line of a constant coordinate psi I. The coordinates are defined by the coordinate transformation xi equal xi of psi j, where j goes from 1 to 3, which is characterized by the Jacobian j. If we select to work with Cartesian-based vectors and velocity vector components, only the derivatives with respect to Cartesian coordinates need to be transformed into non-orthogonal coordinates. This is shown in the next slide. The derivative of phi with respect to xi is equal to the sum of products of derivatives of phi with respect to psi j and the derivative of psi j with respect to Cartesian coordinate xi. Index j varies from 1 to 2 in 2 dimensions and from 1 to 3 in 3 dimensions. The derivative of a non-orthogonal coordinate psi j with respect to Cartesian coordinate xi is equal to the cofactor of delta xi to delta xj in the Jacobian j, which is here denoted as beta ij, divided by the Jacobian. The cofactor of delta xi to delta xij in the Jacobian j is the determinant of the matrix obtained by eliminating the row I and column j from the Jacobian, multiplied by 1 if I plus j gives an even number and minus 1 otherwise. For example, for beta 1, 2, we eliminate the first row and second column from the Jacobian and compute the determinant of the remaining 2 by 2 matrix. This element times this one minus the product of the remaining 2. Because the sum of indexes 1 plus 2 equals 3 is odd, we put the minus sign in front of it. This is now beta 1, 2. The complete list of all 9 cofactors is given here. In 2 dimensions, the expressions are much simpler than in 3 dimensions. The cofactors are just a single derivative of a Cartesian coordinate with respect to non-orthogonal coordinate. For example, for beta 1, 2, we eliminate the first row and the second column, and there remains only this derivative of delta x2 to delta xi1. The derivative of phi with respect to each Cartesian coordinate at node P requires the computation of derivatives with respect to both non-orthogonal coordinates xi1 and xi2 as shown in this expression. The generic conservation equation, which is in Cartesian coordinates given by this expression, transforms into a more complicated expression in terms of non-orthogonal coordinates as shown in the next slide. This is a compact form of the generic conservation equation written in non-orthogonal coordinates. This compact form is obtained by introducing shorthand notation uj and bmj, which represent sums of free products involving cofactors beta ij and Cartesian velocity components ui, as shown in these two expressions. uj is proportional to the velocity component normal to the coordinate surface xij equal constant. The transform momentum equations contain several additional terms. See slides 6 and 7 of lecture 16, but these are transformed in the same way. The transformed generic conservation equation has a similar form as in Cartesian coordinates, only each term in the latter is replaced by a sum of three terms in the former. The partially expanded form of the generic conservation equation transformed to non-orthogonal coordinates is given here. If u's and b's were also expanded in each term, the full complexity would become obvious. The first derivative of coordinates appear in this equation as coefficients, betas in u's and b's. See slides 6 and 7. These are not difficult to evaluate numerically. For example, if we use central differences, we can approximate the derivative of x1 with respect to xi1 at node P as the difference in values of Cartesian coordinates x1 at nodes E and W, divided by the distance between these two nodes in the coordinate xi1. The grid spacing in transformed space is usually taken to be unity. Analogously, the derivative of x1 with respect to xi2 at node P is approximated as the difference in values of Cartesian coordinate x1 at nodes N and S, divided by distance between these two nodes in the coordinate xi2. An unusual feature of the conservation equation transformed to non-orthogonal coordinates is that it contains mixed derivatives of the transported variable phi in diffusion terms. These are the terms including bij with unequal indexes. All three derivatives of phi, which stem from the gradient operator, appear inside each of the outer derivatives, which stem from the divergence operator. See slide 15 of lecture 3. The mixed derivatives are multiplied by coefficients bij with unequal indexes. These become zero when grid lines are orthogonal, irrespective of whether grid lines are rectilinear or curvilinear. For example, these terms are zero in polar, cylindrical, and spherical coordinates, because at every node grid lines are orthogonal to each other. If the grid is non-orthogonal, their magnitudes relative to the diagonal elements bii depend on the angles between the grid lines and on the grid aspect ratio. When the angle between grid lines is small and the aspect ratio large, the coefficients multiplying mixed derivatives may be larger than the diagonal coefficients, which can lead to numerical problems, poor convergence, oscillations in solution, etc. If the non-orthogonality and aspect ratio are moderate, these terms are much smaller than the diagonal ones and cause no problems. The mixed derivatives terms are usually treated explicitly using the third correction approach, that is, evaluated using variable values from previous iteration. The inclusion of mixed derivatives, also called cross derivatives, in the implicit computational molecule would make the latter large and the solution more expensive. In 3 dimensions, implicit treatment of approximations for mixed derivatives based on second-order central differences would lead to 27 coefficients in the matrix, compared to 7 coefficients when the third correction approach is used. See lecture 5, slides 12 to 13. The explicit treatment of cross derivatives usually increases the number of outer iterations, but the savings derived from a simpler matrix and less expensive inner iterations is far more significant. Derivatives in diffusion terms are usually approximated using central differences. The derivatives along curved coordinates are approximated in the same way as those along straight lines. However, if grid non-orthogonality is strong, central difference approximation can cause problems like unbounded solutions, poor convergence, etc. Dimitrich in 1987 recognized that the problem stems from nodes in sharp corners of the computational molecule. In this figure, for a two-dimensional example, these are the nodes SE and NW. He proposed combining forward and backward differences in approximations of inner derivatives. For example, for the situation shown in this figure, we approximate the outer derivative with a central difference, that is, the inner derivative at the east node minus inner derivative at west node divided by the distance. For the derivative with respect to psi2 at node E, we use forward difference, the value at node NE minus the value at node E divided by distance. Central difference would use the value at node SE, which is in the sharp corner, and we want to avoid it. On the other side, for the derivative with respect to psi2 at node W, we use backward difference, the value at node W minus the value at node SW divided by distance. Both forward and backward difference are first-order approximations. However, the errors from forward and backward differences at opposite sides, node E and node W, cancel partially out, leading to a second-order approximation which does not cause problems. See also slide 15 of lecture 4. Coordinate transformations are often presented as a means of converting a complicated non-orthogonal grid into a simple, uniform Cartesian grid. The spacing in transformed space is arbitrary, but one usually takes delta psi I equal unity. Some authors claim that discretization thus becomes simpler, as the grid in the transformed space is uniform. This simplification is, however, illusory. The flow does take place in a complex geometry, and this fact cannot be hidden by a clever coordinate transformation. Although the transformed grid looks simpler than the non-transformed one, the information about the complexity is contained in the matrix coefficients. The discretization on the uniform transformed mesh is simple and accurate, but the calculation of Jacobian, betas and b's is based on the real geometry, and every one of these terms includes a discretization error. Let us see how one can hide the coordinate transformation, that is, avoid assigning values to non-orthogonal coordinates and computing the Jacobian. The grid spacing delta psi I does not have to be specified explicitly. The volume in physical space, delta V, is defined as the product of the Jacobian and the coordinate spacings, delta psi 1, delta psi 2, and delta psi 3. If we multiply the whole transform conservation equation by the product of grid spacing delta psi 1, delta psi 2, delta psi 3, and replace the product of these with the Jacobian everywhere by delta W, the volume of an imaginary cell, then the grid spacing delta psi I disappear in all terms. Assume that central differences are used to approximate the cofactors beta ij. In 2 dimensions, beta 1 is approximated as x2 at node n minus x2 at node s divided by 2 delta psi 2. Analogously, beta 2 is approximated as x2 at node E minus x2 at node W divided by 2 grid spacings. With delta psi I in denominators disappearing after the whole transformed conservation equation is multiplied by the product of grid spacing delta psi 1, delta psi 2, as explained in the preceding slide, the final discretized terms involve only the differences in Cartesian coordinates between neighbor nodes and the volumes of imaginary cells around each node. Therefore, all we need to do is to construct suitable cells around each grid node and calculate their volume in real geometry. The coordinates psi I need not be assigned any value, and the coordinate transformation is hidden. The volumes created around grid nodes should be non-overlapping. A suitable construction of such volumes using lines placed midway between 2 grid lines is indicated in this figure. Finite-difference methods can also be applied to arbitrary unstructured grids by prescribing a differentiable shape function for example a polynomial, which describes the variation of the variable phi in the vicinity of a particular grid point. The coefficients of the polynomial can be obtained by fitting the shape function to the values of phi at a certain number of surrounding nodes. There is no need to transform any term in the equation, so the equations in the simplest Cartesian form can be used. Consider the steady-state generic conservation equation in non-conservative form with a constant diffusivity coefficient gamma given by this expression. The non-conservative form of equations is simpler to use in finite difference methods than the conservative form, which is why it is preferred. See slide 12 of lecture 3 or section 1.4 in the book for a discussion of the two forms of equations. In the next slide, we demonstrate the approach for approximating the first and the second derivative in this equation in 2 dimensions using a biquadratic shape function given by this expression. We now fit the function from previous slide to phi p and its 5 neighbor nodes to obtain coefficients a0 to a5. Note that each coefficient is a function of all 6 variable values. We can now differentiate the shape function twice with respect to x and y to obtain approximations of the derivatives featuring the conservation equation written in Cartesian coordinates as shown in preceding slide. The approximation of derivatives are functions of coefficients a0 to a5 and coordinates at node P. We now insert the coefficients ai in terms of variable values at node P and its 5 neighbors into the above derivatives, then the derivatives into the conservation equation from previous slide. After some rearrangements, we obtain an algebraic equation at node P, which looks the same as the algebraic equation obtained from finite volume or finite difference methods applied to unstructured grids. Note that QP on the right-hand side of the algebraic equation contains the source term QP and possibly some other terms involving known variables, for example at boundaries. One can allow for different shape functions to be used at every grid node depending on the local grid topology and the number of immediate neighbor grid nodes. This leads to a different number of neighbors in computational molecules, but a solver that can deal with this complexity can easily be devised, for example, algebraic multigrid or conjugate gradient type solvers. A finite difference method of this kind does not need a definition of a grid at all. Any set of discrete points adequately distributed over the solution domain would do. One needs to locate a certain number of near neighbors of each point to which a suitable shape function can be fit. The remaining procedure is the same as described above. The non-conservative form of conservation equations, as shown in slide 16, is more suitable for this approach because it is simpler to discretize. It is easier to optimally distribute points in space than to create optimal control volumes or elements of good quality. One of the greatest problems for finite volume methods is the creation of a closed surface of the solution domain. The finite difference method is more forgiving. Any gap between two grid points is simply invisible. In addition, finite volume cells should fulfill certain minimum quality requirements, because otherwise either convergence problems or non-physical solutions or both can arise. The optimization of control volume shape is complicated, and many operations like imprinting of surfaces with non-conformal grid interfaces are sensitive to tolerances. In gridless finite difference methods, shifting single points in space or introducing new ones to optimize their relative positions is easy, as only distances between them play a role. Tolerances are not an issue. Here is a brief summary of this lecture. Finite difference methods are not widely used to simulate flows in complex geometries. In most publications found in literature, finite difference methods are applied to structured non-orthogonal boundary-fitted grids and geometries of moderate complexity. Coordinate transformation is a convenient approach to develop finite difference methods for structured non-orthogonal grids. Diffusion terms contain mixed derivatives when coordinate transformation is applied to non-orthogonal grids. These terms can cause problems if the grid non-orthogonality or aspect ratio are excessive. Finite difference methods can be applied to unstructured grids by using shape functions. No coordinate transformation is needed. shape functions are simply differentiated with respect to Cartesian coordinates. Finite difference methods based on shape functions can also be applied to a cloud of points. It is not necessary to define a grid connecting the points.